Consider this language. L equals 0 power n, 1 power 2n, where n greater than or equal to 1. A slight extension to what we discussed so far. If you look at this language, it consists of strings of the form: if n is 1, then it has this. If n is 2, it has this. And if n is 3, then it has this. Okay, and so on. Now, can we attempt to construct a push-down automaton for this? Let's describe informally before we get into the formal description. So please note, for every 0 there are two ones. For this 0, it corresponds to this, and this one corresponds to this. And I mean, this can be visualized like this. So this 0 corresponds to these two, then this corresponds to these two, then this corresponds to these two. So in the earlier one, it was 0 power n, 1 power n, and for each 0 there was one corresponding one. Whereas over here, for each 0 there are two corresponding ones. So how do we model this? So what we do is the following. When we read 0, so for each 0 we push two capital A's. And when we see a 1, so which means when we read 0 power n completely, so on reading 0 power n completely, what will you see on the stack? The stack as 2n capital A's, because for each 0 we push 2. When you completely read this, there will be 2n A's. And now when you start reading 1 power n, 1 power 2n, you start performing pop. So for each 1, pop capital A. Now if it is valid, then 1 power 2n matches with 2n capital A's, which means it is a valid string. And in case there is a mismatch, 0 is more or 1 is more, then you see that there will be a mismatch, you reject the string. So the idea is this: for each 0 you push 2 A's, which means when we complete reading all zeros, there will be 2n A's. Now when you start scanning 1, for each 1 you pop 1A out. If it is a valid string, there will be 2n A's on the stack and 2n 1's on the input. There is a match, accept. So what am I saying? Suppose the input is 0, 1, 1. When we read this 0, initially it will be Z0, then we push 2 A's. Then this is for this 0. Then we read a 1. On reading the first one, you pop 1A. So configuration will be this. So on reading 1, pop A. When you read one more 1, you pop that as well. This is what happens. Suppose the input is something like this, then for the first 0 there will be 2 A's. Then after that, for the next 0 there will be 2 more. Then we start reading once. For the first one we pop this, For the second one we pop this, third one we pop this, fourth one we pop this. Now if you look at the input, there are 5 ones. Now the control is here and stack contains Z0. Stack is empty and input is not, so you reject the string. It is an invalid input. Okay. On the similar line, you have say 2 zeros and say just 1 1. Then you see that it is Z0. For the first 0 it is 2 A's. For the next 0 it is 2 more. Then when we read this one, we pop this A out. Now control is here. Now input tape is empty. Stack is not. Stack has some more A's, which means it is invalid input, reject. Which means on finishing, when you start scanning the input from left to right, once you exhaust the input on reading the input completely, then stack must be empty. If you see that there are symbols left in the stack, then it is invalid, or stack is empty and the input tape is not empty, then also it is invalid. So that is all. So we have given an informal description. Now let's formally define this using transition diagram and transition function. So here is the description. Delta of Q0, 0, start symbol is Z0. We go to Q1, we push, remember for each 0 we push 2 symbols. Yes. We generally write top 2 symbols of the stack. Now just for clarity purpose I have written this. Either you can write like this or you just mention Q1, AA. Okay. So now I am in Q1. I read some more zeros. Top of the stack will be A, because for this you would have pushed A's. Now Q1, stay in Q1, push 2 more A's. You already have 1. On top of it, you push 2 more. Or you write Q1, AA. Both are correct. So now you have completed reading zeros. Now go to 1. I am in Q1, reading a 1. Top symbol is A. Then I say Q2, epsilon. This means pop A. Now I am in Q2. You read a 1. Top symbol is this. Continue to pop. Now at the end of this you will see 2n A's and this starts performing. Supposing it is a valid input, which means you will be at Q2 and input is exhausted, top symbol is Z0, then you say accept. Fine. So this ensures 2n A's are pushed onto the stack, and which means when you start scanning once, you see that there are 2n A's on the stack. If it is a valid string, you will exhaust the input, which means 2n A's are popped out of the stack. The top of the stack will be Z0. You accept and reach the final state QF. You can also empty the stack. You can write this or empty this. There are 2 ways of accepting this. This one as acceptance by final state, very similar to what we do for finite automata. This one is acceptance by emptying the push down store. You even empty the stack. So acceptance by empty stack, or it is also known as empty store in the literature. Both are equivalent. Either you can write this or you can write this. Now there are a couple of more transitions which will capture the invalid inputs. For example, when we are at Q0, we read 1, top symbol is Z0, then we must reject. So we go to a state called QR. That is one case. Then when we are at say Q2, we look for 1, but you see a 0, top symbol is A, then it must be rejected. Or you are at Q2, you come across 0, top symbol is Z0, then also you have to reject. This ensures if an input starts with 1, it has to be rejected, that is taken care of. And when you are seeing 1, you also come across some 0. It is like 0, some 1s, then you come across a 0. For example, 0, 0, 1, 1, 1, you see a 0. And when you start reading these ones, you will be at Q2. And you see that Q2, 0, top of the stack is A, then it must be rejected. Or it is like 0, 0, 4 ones, then you see a 0. So you are at Q2 and top of the stack is Z0, then it must be rejected. Or the input starts with 1, 1, 0, 0, something like this, then it must be rejected. That is taken care by this input, this transition. Fine. So this completes the formal description of this language. One can construct a transition diagram out of this, and most importantly a context-free grammar out of this, which we shall see next. Let's construct CFG for this. Remember, if you look at the pattern 0, 1, 1, 0, 0, 4 ones, which means each 0 corresponds to 2 ones. Okay. Now somehow this has to be captured as part of our recursive definition. What I do is the following. The simplest string is S imply 0, 1, 1, and S implies 0, S, double 1. That's my recursive definition. Now you see that for every 0 you have 2 ones. Now you want to generate input like this, for example 0, 1, 1, then simply use S imply 0, 1, 1. You want to generate this, then first take S imply 0, S double 1, then replace this with this, so it becomes 0, 0, double 1, double 1. Now you want to generate 0, 0, 0 followed by 6 ones, then apply this, then replace this with the same production. It becomes this. Now you have decided to stop the recursion, use the other one. So in general, to generate 0 power n, 1 power n, what do we do? Use s imply 0 s double 1 n minus 1 times followed by s imply 0 1. So this gives you the recursive part for n minus 1 times or iterations, and you want to end the recursion, so use this. Now the class of languages accepted by this grammar, the succinct representation, this grammar is precisely this, and there is an equivalent PDA as well, which means given a language, one can construct a CFG, one can construct the corresponding PDA as well. Now let's fine tune, and can we look for some other comparison between 0 and 1. For example, 0 power n and 1 power m, and say m is n square, m is n factorial, and some other comparisons. We say m is between n and 2 power n. So things like that will PDA accept? Can we construct an equivalent context-free grammar? All that we shall discuss. And so for this language, we have seen transition function and a context-free grammar. Transition diagram is similar to what we did. So we start from Q0 and we read a 0. On reading a 0, top symbol is Z0, which is changed to AA Z0. We go to Q1. And at Q1, we read some more zeros. Top symbol is A. Then that is replaced with we are not replacing, we push some more A's, so it becomes this. Then we read a 1 and top symbol is A. We perform pop, go to Q2. At Q2, we read remaining zeros and we pop, so we read remaining ones and we pop A out of the stack. And from this, when you know you have exhausted the input, top of the stack is Z0, you reach QF and accept. In between, you come across a 0 here or 1 here, you reach QR. Okay. So that's precisely the model. Now we want to understand its computing power limitations. So through these examples, we will experiment and understand the limitation of the machine. Let's look at another variant of this language.